Hello everyone, this is Dr. K. Evangelie Supriya, working as an associate professor in the Department of Humanities and Science, SRIT Engineering College, Anantapur, Andhra Pradesh. Today I am going to give you a video lecture on Engineering Physics syllabus, unit number 4. We have quantum mechanics and free electron theory. So before going to learn about the things, we should know about the wave particle duality. Universe is composed of matter and radiation. Since nature loves symmetry, matter and radiation must be symmetric. Particle possess mass, velocity, momentum and energy, whereas wavelength, frequency, phase, amplitude and intensity are the characteristics of a wave. The particle nature of light can be understood from photoelectric effect and Crompton effect, whereas the wave behavior of light can be observed in interference, diffraction and polarization. We should know what do you mean by wave. Wave is nothing but a disturbance of the medium. The properties of the waves included, we have diffraction, interference, polarization, superposition, diffraction, etc. Wave, hence the light is having the dual nature. De Broglie's hypothesis: if radiation like light, which is a wave, can act like a particle, then why not material like particles can act like a wave sometime. So this hypothetical idea made the scientist de Broglie to suggest the radiation matter in 1923, which also having the dual nature. This is based on the fact that nature is symmetrical and hence material particles should also act as waves at time. So every moving particle is associated with a wave called matter waves. The wave nature associated with the moving particle is known as matter waves. Matter waves has both particle and wave nature called as duality. According to the de Broglie hypothesis, the lambda, that is wavelength, is given by h by p, where h is the Planck's constant and p is the momentum, which is also known as h is equals to lambda is equals to h by mv. From Planck's theory, we have E is equals to hv. According to the Einstein theory, we have E is equals to mc square. Then equating 1 and 2, we will get the lambda is equals to h by mv. We know that the kinetic energy is equals to half mv square. Then we will multiplying and substituting all those things, we will get the equation. De Broglie wavelength lambda is equals to h by square root of 2me into ev, where h is the Planck's constant, which is a constant 6.625 into 10 to the power of minus 34 joule per second. Me is the mass of electron 9.1 into 10 to the power of minus 31. E is the charge of electron 1.6 into 10 to the power of minus 19. After substituting all the values, we will get the value wavelength lambda is equals to 12.26 by root V Armstrongs. So these are the some of the properties of the matter waves we have enlisted here. Lighter is a particle, greater is the wavelength associated with it. When V is equals to 0, lambda is equals to alpha, then wave becomes undetermined. If V is equals to alpha, then lambda is equals to 0. Lambda is equals to h by mv is independent of charge. This shows that these waves are not electromagnetic waves. Velocity of matter waves depend on the velocity of the particle. The wave velocity of matter waves is greater than the velocity of the light. Mu is equals to c square by v. So we have to determine the wave function. A variable quantity. What do you mean by wave function? It is a variable quantity which characterizes the de Broglie's waves, which is known as wave function, and it is denoted by symbol psi. The value of the wave function associated with a moving particle along the axis xyz with time t gives the probability of finding the particle at time t at that point. So the physical significance here, the points we have here is the wave function has no physical meaning. It is a complex quantity representing the matter wave of a particle. Psi square is real and positive, and but the intensity is always real and positive. For a given volume, we have P is equals to psi square into dt. The probability lies between 0 and 1. We have the conditions for the orthogonal and normalized wave function. Now, next we have the Schrödinger wave equation. So, Austrian scientist Erwin Schrödinger firstly described the wave nature of the particle derived in the mathematical form, which connects the expression of de Broglie wavelength with classical wave equation. Schrödinger wave equations has two forms. One is time independent wave equation and time dependent wave equation. We have to, for the Schrödinger wave equation, independent equation, we have to consider a particle of mass m with a velocity v along the x direction. Then we have the displacement is given by psi of x comma t is equals to a e power I of kx minus omega t, where we have a is the amplitude of the wave, k is the wavelength, 2 pi by lambda, omega is equals to 2 pi into gamma. Now, after differentiating all the equations, we will get the de Broglie hypothesis. We have lambda is equal to h by mv, and we have both kinetic energy and potential energy. And after substituting, we will get the equation dou square psi by dou x square plus 2m by h cut square into e minus v into psi. This is the Schrodinger one-dimensional time independent wave equation. Dou square psi by dou x square plus 2m by h cut square into e minus v into psi is equals to 0 represents the Schrodinger's one-dimensional time independent wave equation. Suppose if you want for three-dimensional equation, we have del squared psi plus 2m by h cut square into e minus v into psi is equals to 0, where del square is equals to, because we are talking about three-dimensional motion, we have it is having along the three axis x, y, z. Del square is equals to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. And then particle, again we have determined the Schrodinger equation in one-dimensional equation. We have particle in one-dimensional box. For that, consider a particle of mass m moving back and forth, as you can see here, inside a potential box of infinite height and length as shown in the figure below. As the particle is moving freely inside the box, it is associated with a wave, and its position is represented by a wave function psi. Here we are having the boundary condition. Suppose whenever you are talking about the particle in a one-dimensional box, this boundary conditions plays a key role. We have here v of x is equals to 0. Well, 0 is less than x less than a, psi is not equals to 0. Suppose v of x is equals to infinity, 0 is greater than or equals to x or greater than or equals to a, where psi is equals to 0. To find the wave equation of a particle within the box of width a, consider a Schrodinger's one-dimensional time independent wave equation. In the we have derived already Schrodinger one-dimensional equation. We know that for del square psi plus 2m by h cut square into e minus v into psi is equals to 0. So this is a Schrodinger time independent equation. After that, here we are having the energy, potential energy inside the box is 0. The particle has kinetic energy alone, so it is named as a free particle or free electron. So we have dou square psi by dou x square plus k square is psi is equals to 0. For second order differential equation, the solution for the above equation is given by psi of x is equals to a sin kx plus b cos kx. So when you apply the boundary conditions, we will get the sin n is equals to a sin n pi by a into x. So this is the boundary conditions. For that, we will get E1 is equals to h square by 8ma square. That is when n is equals to 1. So energy of the particle in one-dimensional box, we got determined En is equals to n square h square by 8ma square. Suppose if we substitute n is equals to 1, 2, 3, we will get the corresponding energy values. E1 is equals to h square by 8ma square, E2 is equals to 4h square by 8m square, E3 is equals to 9h square by 8m square. So each energy value is also known as eigenvalue, and the corresponding wave function to that respective energy value is nothing but eigen wave function. Again, for the normalization of the function, we have the condition. Here normalization is the process by which the probability of the finding the particle is done. Suppose if the particle is definitely present in a box, then P is equals to 1. Then substituting all the values, we can see here the energy levels with respect to wave functions in figure A, and with respect to probability density, as you can see the variation here clearly. And thus therefore the normalized wave function is given by psi n is equals to root 2 by a into sine of n pi by a into x, where En is the known as normalized eigen energy. En is equals to n square h square by 8ma square. Normalized wave function psi n is equals to square root of 2 by a into sine n pi by a into x. Next topic is a free electron theory. So we have two types of free electron theory. One is the classical free electron theory and another one is quantum free electron theory. So this classical free electron theory, it was first developed by the scientists Drude and Lorentz in 1900. According to this theory, metal contains free electrons which are responsible for the electrical conductivity, and electrons obeys the laws of classical mechanics. In the quantum free electron theory, this was developed by the scientist Sommerfeld in 1928. Developed according to his theory, the free electrons move with a constant potentials. This theory obeys quantum laws. First, we have to study the classical free electron theory of metals, which is also known as a Drude-Lorentz theory of metals. So what are the assumptions and salient features of the classical free electron theory? In metals, there are large number of free electrons moving freely in all the directions. These free electrons, like gas molecules in a container, obeying the laws of kinetic energy theory of gases. Even in the absence of electric field, the energy associated with each electron at a temperature T is given by 3 by 2 kT, which is also equivalent to half mv square. In metals, the positive ion cores at a fixed positions, and the free electrons of the conduction and the free electrons move randomly and collide either with positive ion cores or other free electrons with boundaries. Electron velocities in metals obeys the Maxwell-Boltzmann distribution of velocities. The free electrons move in a constant potential field. So when an electric field is applied to a metal, free electrons are accelerated in the direction of opposite direction of applied electric field with a velocity called drift velocity, represented known as Vd. So the electrical conductivity in metals, for that let us consider of length L and area of cross section A. Then the volume of the conductor is given by Al. If there are number of electrons per unit volume of the metal, the total number of electrons in the metal is given by Aln. So we are having the charge here, Aln E by T, and we have the drift velocity Vd is equals to J by Ne. And again, after from Newton's second law, we have F is equals to Ma. Equating all the equations, we will get the value of conductivity. J is equals to sigma E. So on comparing equation 4 and 5, we have the conductivity formula. Sigma is equals to Ne square by M into Tc. So conductivity may also be expressed in terms of mobility mu, which is also known as drift velocity per unit electric field. Mu is equals to Vd by E, sigma is equals to Ne nu. We can see here the drift velocity Vd, it is the average velocity acquired by the electrons in a direction opposite to the direction of the applied electric field, which is given by Vd is equals to E into tau by M. Mean free path, the average distance travelled by the conduction electrons between two successive collisions with lattice ions is known as mean free path. So if we consider the C with the RMS velocity, we will have C bar is equals to square root of 3 kT by M. For that, sigma is equals to n lambda E square by square root of 3 mkt. So the relaxation time we have here, under the influence of an electric field, free electrons attain a directional velocity of motion. If the field is switched off, the velocity starts decreasing exponentially. Such a process that tends to restore equilibrium is called relaxation process. We have V is equals to V naught e power minus T by TR, where TR is the relaxation time. As you can see here, we have plotted the graph between time and drift velocity Vd. We can see how the graph is decayed. Thus, we can say the relaxation time is defined as the time required for the electron to reduce its velocity to 1 by E of its initial value. And again, we have some of the merits of classical free electron theory, as it verifies Ohm's law, it verifies electrical and thermal conductivities of the metals, it derives Weidmann-Franz law, it explains optical properties of the metals. These are some of the merits. Of course, there are demerits also there for the classical free electron theory. That demerits can be covered by the quantum free electron theory. So the demerits involves, it fails to explain the electrical conductivity of semiconductors and insulators especially. It fails to explain the temperature variation of electrical conductivity at low temperature, and it fails to explain the concept of specific heat in metals. It fails to explain the mean free path of electrons. The phenomenon like photoelectric effect, Crompton effect, and black body radiations, these phenomenon could not be explained by the classical free electron theory. So to overcome the failures of the classical free electron theory, again one scientist named Sommerfeld in 1928 came up with an idea of quantum free electron theory. This theory overcomes many of the drawbacks of the classical theory. Sommerfeld explained them by choosing the Fermi-Dirac statistics, where in the Drude and Lorentz, when it comes to the classical free electron theory, they choose the Maxwell-Boltzmann distribution. When it comes to the quantum free electron theory, they have chosen the Fermi-Dirac statistics instead of Maxwell-Boltzmann statistics. So what are the assumptions of the quantum free electron theory? Valence electrons move freely in a constant potential within the boundaries of the metal. So the distribution of electrons in various allowed energy levels occurs as per Pauli's exclusion principle. The attraction between the free electrons and the lattice ions and the repulsion between electrons themselves are ignored. The distribution of energy among the free electrons is according to the Fermi-Dirac statistics. The energy values of the free electrons are quantized. To find the energy values of electrons, Schrodinger time-independent wave equation is applied. This problem is similar to that of particle present in a potential box. So to overcome this drawbacks of classical free electron theory, he treated electron as a quantum particle. This electron follows the principles of Pauli exclusion principle. What exactly this Pauli's exclusion principle means? No two electrons will have the same quantum state. So the maximum velocity of electron at highest occupied level, that is Fermi level, is known as the Fermi velocity, which is denoted by Vf and is represented by the radius of the Fermi sphere. Even in the absence of the electric field, these velocities cancel each other and net velocity in all directions becomes 0. As you can see, these are the figures indicating here, and the relation between P and wave vector P is equals to h cut k. So by integrating and differentiating the above equation, we will get the sigma is equals to Ne square by Tf into n. So thus how the above equation represents the electrical conductivity according to the quantum free electron theory, which follows the Fermi-Dirac statistics and Pauli's exclusion principle by Sommerfeld in 1902. This quantum free electron theory especially overcomes the drawbacks of the classical free electron theory. And again, it has some of the merits of this theory. It successfully explains the electrical and thermal conductivity of metals. It explains the thermionic phenomenon. It explains the temperature dependence and conductivity of metals. It explains the specific heat of metals. It explains the magnetic susceptibility of metals. It can explain the photoelectric effect, Crompton effect, and black body radiation. It gives the correct mathematical expression for the thermal conductivity of the metals. There are also some demerits for this quantum free electron theory also, because it is unable to explain the metallic properties exhibited by only certain crystals, unable to explain why the atomic arrays in metallic crystals should prefer only certain structures. It fails to distinguish between metal, semiconductor, and insulator. It also fails to explain the positive value of the Hall coefficient. Only 2 electrons in the Fermi level, and they are responsible for the conduction, which may not be true. These are some of the demerits of the quantum free electron theory developed by Sommerfeld in 1902. And next one is Fermi-Dirac distribution. In a metal in absence of electric field, free electrons move at random, similar to the behavior of the electron gas. Since electrons are indistinguishable particles and have spin, they are also known as Fermi particles. Hence, such electron gas obeys the Fermi-Dirac statistics or distribution. The Fermi-Dirac distribution describes the behavior of free electron gas taking into account the quantum theory of Pauli's exclusion principle, that is not more than 2 electrons can occupy the same energy level. Even at absolute zero temperature, 2 electrons occupy the ground state, and two into each state are of next higher energy levels. The highest energy level occupied by electrons at absolute zero is known as Fermi energy level, which separates the occupied states from the unoccupied states. That is how the value energy of the Fermi level is denoted by E suffix f. We have f of E is equals to 1 by 1 plus exponential of E minus Ef by Kb into 2, where Kb is the Boltzmann constant. How this effect on temperature, how the temperature affects on Fermi-Dirac distribution function. Here we are having the variation of Fermi factor with energy and temperature, that is f of E. Here we have two conditions. One is T is equals to 0 Kelvin, and for E is less than Ef. And again case number 2, we have E is greater than Ef and T is equals to 0 Kelvin. For that we have f of E is equals to 1 at E is less than Ef, and f of E is equals to 0 at E is greater than Ef. This implies that at absolute temperature all the energy levels above Ef are unoccupied, that is, which are completely empty, which is true form of the definition of the Fermi energy. Again we have case number 3, E is equals to Ef. For that we will get f of E is equals to indeterminate, and we have E is equals to Ef at T is greater than 0 Kelvin, f of E is equals to 1 by 2. We can see here we have drawn the graph against E is equals to Ef value and f of E. We can see there are variations happening here at T is equals to 0 Kelvin and T is greater than Kelvin. So if E is less than Ef, the probability starts from decreasing from that is 0.1, you can see here, and it reaches against to again to 0.5, you can see in the graph, and then it will falls at E is equals to Ef, and for E is greater than Ef it further falls as shown in the figure. In this conclusion, the Fermi energy is the most probable or average energy of the electrons in a solid. The variation of the Fermi factor with energy and temperature is shown in the figure below. So again we have sources of electrical resistance. So there are some sources for the electrical resistance. According to the quantum free electron theory, the free electron while the moving at random within the metal gets scattered by the positive ions in the metal, and this scattering may occur due to the some other factors like impurities and imperfections in the material or metal. So the scattering of electrons in the conductors is because of three sources. One is lattice vibrations, which is also known as phonon scattering, and the other one, second one, is by the impurities, and the third one is by structural imperfections. So under normal conditions without applied electric field, the positive ions will be in vibrations about their mean positions due to thermal energy. How these vibrations are known as lattice vibrations. Suppose when the moving electrons encounter the vibrating positive ions, they get scattered. This type of scattering is known as phonon scattering. So what exactly means, when the moving electrons encountering the vibrating positive ions, they get scattered. This scattering is nothing but the phonon scattering. So due to the impurities or impurities present in the metal, and due to the effects, the electrons also gets scattered. The above scatterers acts as a source of electrical resistance for the metal. Suppose we can take at room temperature, the resistivity of the metals is independent of impurities and imperfections and varies proportional to temperature. Even at the very low temperatures where T is tending to 0 Kelvin, it would except the conductivity become infinity in pure metals, but the lattice vibrations are not limiting. So the resistivity in metals varies T power 5 near 0 Kelvin. So there are three sources of electrical resistance we should remember. One is lattice vibrations, also known as phonon scattering, and the other one is by the impurities, and the other one is by structural imperfections. So the general characteristics of the electrical resistance in metals are summarized as follows. You can see here the electrical current density in the steady state is proportional to the electric field strength, which is known as Ohm's law. For pure specimens, the electrical resistivity varies with the temperature. Rho is directly proportional to temperature at high temperature. For metals containing all amounts of impurities, the electrical resistivity rho may be written as rho is equals to rho naught plus rho into Pt, where rho of rho Pt is the temperature dependent of the resistivity. For most metals, the electrical resistivity decreases with increasing pressure. Again, we have origin of energy bands. How this energy bands is originated. In an isolated atom, the electrons are tightly bound and have discrete sharp energy levels. Suppose, as you can see here, when two identical atoms, as you can see in figure number B, here we have two identical atoms are brought closer to each other. The outermost orbits of these atoms, as you can see, this is outermost orbit of two atoms. When they brought closer to each other, and then overlap, the outermost orbits of these atoms overlap here and interact, then the energy level splits into two. If more or two atoms brought together, as you can see in the figure number C, in figure number B we have only two atoms, in the figure number C we have three atoms, that is more than two atoms. If more atoms are brought together, more levels are formed, and for a solid of n atoms, suppose you can take that like n number of atoms, each of the energy levels of an atom splits into n levels of energy. These levels are so close to each other that they form an almost continuous band. The width of this band depends on the degree of overlap of electrons of adjacent atoms. As you can see, more number we have taken, first is one atom, and second figure two atoms, and the third figure n number of atoms. Then we have the n number of n levels of energy, and they together form a continuous band. The width of this band depends on the degree of overlap of electrons of adjacent atoms and is largest for the outermost atomic electrons. So as you can see, in the solid substance, the interatomic distance is very small, hence there is a strong interaction between any two successive atoms. Due to this interaction, the energy levels of all the atoms overlap with each other, and hence a continuum is formed. This continuum then separates into two bands, namely the valency band and the conduction band. Between the distance between conduction band and the valency band is nothing but energy gap. We can see the valence electrons are occupied especially in the valence band, since they are responsible for electrical, thermal and optical properties of solids. Above the valence band, the conduction band is vacant at 0 Kelvin. According to the width of the gap between the bands and band occupation by electrons, all solids are classified broadly into three groups, namely metals, semiconductors and insulators. We can see here we have plotted a graph between interatomic distance and energy. There is a formation of conduction band on the upper side, and the lower side it is having the valence band, and the distance between these two bands is nothing but energy gap, which is a band gap, which is denoted by Eg, and the conduction band is denoted by Ec, and the valence band is denoted by Ev. Next, classification of solids. So on the basis of the magnitude of the forbidden band, the solids are classified into metals, semiconductors and insulators. First of all, we should study about the metals. There is no forbidden band and valence band. There is no forbidden band, and the valence and conduction band overlap each other. So in conduction band, plenty of free electrons are available for the process of electric conduction. The electrons from valence band freely enter into the conduction band. The most important point in the conductor is that due to the presence of forbidden band, there is no structure to establish holes. The current in the conductor is simply as a flow of electrons. We can see here valency band and conduction band. Eg is greater than 5 electron volt in the insulator. And again in the conductor, we can see here Eg is equals to 0, and in the semiconductor Eg is equals to 1 electron volt. And again in the semiconductor, the forbidden gap, you can see the Fermi level here, the distance between conduction band and the valence band, the distance is very small, where Gi and germanium and silicon are the two best examples of the semiconductor. A semiconductor is a material whose conductivity lies between insulator and conductor. A semiconductor is a material who will allow the flow of current partially. So in germanium, the forbidden band is the order of the 0.7 electron volt, while in case of silicon it is 1.1 electron volt. Actually, a semiconductor material is one whose electrical properties lie between insulator and good conductors. At 0 Kelvin, there are no electrons in conduction band, and valence band is completely filled. When a small amount of energy is supplied, the electron can easily jump from valence band to the conduction band. Again, coming to the insulator, the forbidden energy gap is very wide. You can see here, this is the conduction band, this is the valence band. The gap between these two bands is completely very wide and large. So due to this fact, the electron cannot jump from valence band to conduction band. In insulators, the valence electrons are bound very tightly to their parent atoms. The valence band is completely full at 0 Kelvin, and the energy gap between valence band and the conduction band is the order of 10 electron volt. Even in the presence of high electric field, the electrons do not move from one band to another band. When a very large energy is supplied, an electron may be able to jump across the forbidden gap. Increases in temperature enables some electrons to go to the conduction band. This explains why certain materials which are insulators become conductors at high temperatures. As you can see, these are the differences between conductors, insulators and semiconductors we have enlisted in the table. Whereas coming to the conductors easily conducts electrical current and conducts the electrical current less than the conductor and greater than insulator, and in insulator it does not conduct any current. Coming to the conductors, it has only one valence electron in the outermost orbit. Semiconductor has 4 valence electron in its outermost orbit. It has 8 valence electrons in the outermost orbit of insulators. Conductors formed by using metallic bonding. Semiconductors are formed due to covalent bonding, and insulators are formed due to ionic band. So valence band and conduction band are overlapped in conductors. Valence and conduction bands are separated by forbidden energy gap of 1.1 electron volt, and valence band and conduction band are separated by forbidden energy gap of 6 to 10 electron volts. In coming to the conductors, resistance is very small. In semiconductors, resistance is high, and insulators resistance is very high. Coming to the conductors, it has a positive temperature coefficient. In semiconductors, it has negative temperature coefficient, and insulators have a negative temperature coefficient. Examples of the conductors are copper and aluminum. Examples of the semiconductors are silicon and germanium. Examples of the insulators are mica and paper. This is how we can study the classical and quantum free electron theories in unit number 4 of engineering physics. And also we have known the Fermi-Dirac distributions, classical and quantum free electron theory, merits and demerits, and what are the drawbacks, and then effect of temperature on Fermi-Dirac distribution, sources of electrical resistance, origin of energy bands, and classification of solids. Thank you.